Greetings, Brian here. I would like to share some initial ideas regarding a software architecture for building distributed applications. As distributed apps are nicknamed dApps, maybe this architecture can be nicknamed a Darchitecture. Before we proceed, I should clarify these materials are presented for general interest, stimulus for discussion, and public amusement only. None of this material should be interpreted as advice or solicitation. These materials are released open source under an MIT license. Let me begin with a few of the architectural goals, specifically those that distinguish decentralized apps from other applications. All applications have code and data. A decentralized application copies all those assets and spreads the copies across multiple computers. This ensures the system as a whole will continue to provide service if any computer, or even a minority group of computers, fails. The third goal is security. A user's identity is simply a cryptographic token, the public key of a key pair for which the user holds the private key. This pair is used to encrypt and sign all messages exchanged between the user and the application. The fourth goal is open access. Anyone with a device and network connection is able to be a user. Anyone may choose to offer computing power to run the system and be financially rewarded for doing so. The fifth goal is scalability. dApps are openly available to anyone in the world, so there are billions of potential users. There could be any number of them on the system at any given time, so the Darchitecture has to plan for something of the order of 1,000,000 concurrent users. Now consider that some of those users may actually be other computer programs or bots that might use the system more frequently than a human user would. Our Darchitecture begins with a high-level categorization scheme to organize the software along technology lines. Let's start with a green shape representing software that enables external entities to access the system. This area includes the programs that users download from an app store such as Play Store or iTunes, and runs on their personal devices ranging from smartphones to desktops and other platforms. This area also includes the APIs that enable external programs to connect. Next we have a gray shape representing Ethereum. This technology provides one world virtual machine that runs programs called smart contracts concurrently across millions of computers. This provides excellent scalability and fault tolerance. Ethereum also provides a cryptocurrency that enables the system to exchange money with the outside world. Smart contracts in this area will enable users to pay for service and suppliers to get paid. Although smart contracts are highly available, they are slow and expensive and cannot send messages outside of the VM. The next area includes software services that do what Ethereum can't do efficiently. These services are deployed on an anonymizing network such as Tor or perhaps I2P. dApp services will need to store large amounts of dynamic operational data, including such things as accounts, orders, shipments, complaints, and payment records. Ethereum is cost prohibitive in this regard, so the Darchitecture includes software for storing and retrieving operational data. There will likely be operational resources that seldom change, if ever, yet need to be delivered to other software. The Interplanetary File System, or IPFS, is one technology that provides a way to deliver static and semi-static assets without relying on one web server, and without revealing the location of the server. There is an emerging technology called Golem Network, which is a worldwide service enabling anyone to run jobs, and pay for that service using Ethereum. This computer for hire service, currently in development, may provide a way to offload heavy processing from our hidden services. The red area represents software deployed on the traditional World Wide Web and Internet. This includes the sites and web apps through which users discover, register, and install the dApp. It is also how users get information and obtain support. This area may include websites, wikis, user forums, and social media pages. Now, some folks might view these four middle boxes as a business logic layer over a data layer, implying a classic three-tier architecture. Our Darchitecture proposes that the data services be implemented using a distributed ledger or blockchain so that storage does not rely on one instance. Let's take a closer look at the access logic area of the Darchitecture. The software running on the user's device interacts with Ethereum to send and receive money, to query smart contract attributes, and to cause contracts to execute transactions. Simply fetching attributes from Ethereum is a synchronous operation, but running a transaction is asynchronous. Results of execution can be sent to the access logic using Ethereum's event mechanism. User devices are not capable of running a full Ethereum node, as the data requirements are in the hundreds of gigabytes range, so access logic will have to interact with Ethereum using a remote node. The access logic may require static and semi-static resources. It may fetch such assets using interplanetary name system and file system using standard HTTP GET requests. IPFS provides redundant distribution using BitTorrent and security by masking the server's location and representing resource names as hashes. Clients will run web browsers to access standard web resources and web applications to carry out the non-operational use cases. Now let's take another look at the business logic related areas, including the smart contracts, hidden services, and Golem network. The hidden services interact with smart contracts using the same mechanisms employed by the access layer. The hidden services will receive events sent through Ethereum by the clients. Services will perform the requested operations and then push the results back to the clients, again through Ethereum. Note there is no steady-state connection between clients and the hidden services. Should there be computing-intensive tasks, the hidden services may assign jobs to Golem and receive results from Golem by asynchronous communication. Hidden services will then push the results back in the same way as if they did the work themselves. Clients are not aware of Golem and how the work actually gets done. They simply receive the results. The hidden services will store and retrieve operational data using the data services and may retrieve static resources through IPNS/IPFS. As mentioned previously, anyone may choose to provide computing resources to support the system operation. In blockchain and distributed systems, this is called mining, and nodes that do this work are called miners. Let's imagine hidden services and data services deployed together with an Ethereum full node and call this bundle a miner. The full node interfaces the miner with the Ethereum network and provides remote node service to connected clients. Recall that clients are too lightweight to include their own full node and rely on miners to provide this service for them. We will need many such nodes to provide a reasonable level of service to support our large population of clients. Each miner may concurrently serve 0 or any number of clients and should expect multiple requests per second. Miners also communicate with one another to collectively implement a private blockchain in order to provide the distributed data services. Miners will require compensation for electricity, network use, and computer hardware. They will also have to pay Golem for running their jobs. Miner compensation will come from a share of fees paid by users of the dApp. Conway's law reminds us of the relationship between the design of any software system and the structure of the organization that builds it. We feel that the relationship is and should be bidirectional, that the organizational structure does drive design, and also that design defines an optimal organizational structure for implementing that design. We therefore recommend that any organization working on building a distributed app may wish to organize the software development team roughly based on the architectural definition that we have presented so far. This has been a brief high-level look at a potential architecture for building distributed applications. We began by identifying the distinguishing architectural goals. We then identified and described the initial software areas and briefly described the mechanisms by which they interact. Thanks for your attention, and we hope to provide more architecture definition and information in the future.